Out of plane instability refers to buckling of a portion of a wall section out of plane under in-plane actions. As you can see, this portion is limited to end region of the walls or boundary regions where the strains from in-plane actions are greatest. This mode of failure was observed in experiments, but became an important issue after it was observed in the Chile earthquake and the 2011 Christchurch earthquake. In terms of design provisions, New Zealand design standard is the only design standard which has like a clause specifically related to this mode of failure. So the minimum thickness of walls for axle loads greater than 5%, so axle load ratio is greater than 5%, needs to be limited to this value. This actually design provision is developed based on an analytical model developed by Pauli and Priestley. And the buckling length is one of the assumptions here, which is considered to be equal as a theoretical length of the plastic hinge. So we're going to discuss these actual assumptions later, but just like to let you know, there is a provision in the New Zealand concrete design standard specifically related to this mode of failure. So as I said, this design provision was developed based on the analytical study by Pauli and Priestley. And since there were not many experiments which had this mode of failure, some assumptions had to be made. One of these assumptions was the buckling length, as I just said. And a stability criterion was developed based on the stability of the wall cross-section when the cracks close and the out-of-plane deformation starts. And again, the buckling length was assumed to be equal to the theoretical plastic hinge length. Then a study by Chai and Elier confirmed the findings of the previous study. In this study, wall boundary zones were tested. These boundary zones actually represented boundary zones of rectangular walls. They were tested under axial, tensile, and compressive forces. And the same stability criterion was used. And again, the buckling length was assumed to be equal to the plastic hinge length. In terms of numerical studies, we developed a model in 2014 which could capture this mode of failure. The element we used to capture this mode of failure is called curved shell element. This element, unlike flat shell elements which have integration points on the reference plane, only have integration points across the thickness and can therefore capture variation of strain across the thickness and the out-of-plane deformation. This model has been used by other research groups to capture the out-of-plane instability of rectangular walls since then. To verify the model, we used experimental results of wall specimens that had different shear span ratios and therefore different failure modes. The model could capture most of the failure modes observed in the experiment, except for bar buckling at the base, which could not be successfully captured. So as you can see in this plot, the strength degradation observed in the experiment was not captured by the model. However, the out-of-plane deformation and instability was well predicted. For further verification, we used test results of specimens that had out-of-plane instability as the main failure mechanism. On top of this, we actually used this model in a blind prediction practice and predicted the response of a singular reinforced wall specimen that was tested in Switzerland. So to actually understand the failure mechanism predicted by the model and the controlling parameters, we did a bunch of parametric studies and investigated the local response of the reinforcement and concrete elements at different locations, particularly at the location where the out-of-plane deformation was maximum. So to put it in a nutshell, the failure mechanism is captured by the model, follows these steps. So when a structural wall is subjected to lateral loading at large in-plane curvature demands, cracks form in the tensile boundary regions, and then the bars are forced to yield in tension. When the loading is reversed, the cracks are still wide open. However, the tensile forces are now changed to compressive forces, and since the cracks are still wide open, the rebars are the only elements that are resisting against axial forces. So these bars yield in compression, and when the compression occurs across sufficient length and height of the wall, then the model defines the deformation pattern that requires less energy, which is the out-of-plane deformation. However, depending on the initial tensile strain developed in the bars, different scenarios can occur. If the initial tensile strain is less than a specific value, let's say critical strain, then the cracks can close before progression of out-of-plane instability, which reestablishes the contribution of concrete to the load-carrying capacity of the section, and the out-of-plane deformation recovers. However, if the initial, and here you can see the out-of-plane, and here we can see the out-of-plane deformation graph increasing and then decreasing. So, however, if the initial tensile strain is more than the critical strain, then this timely crack closure cannot occur, and the out-of-plane deformation changes to out-of-plane instability. So if we plot the out-of-plane history for this case, then the out-of-plane deformation increases and changes to the instability of the wall. So for a given thickness, there is a critical value for strain which can induce out-of-plane instability. And to control this out-of-plane instability, we need to either increase the thickness, or if we cannot increase the thickness, then we need to limit the strain. So the parameters that are governing this mode of failure are first the wall thickness, or let's say slenderness ratio. What I mean by slenderness ratio is the unsupported height to thickness, because as you know, the unsupported height is also a key parameter. But since like the unsupported height of walls or the story level is sort of constant in structures, we are dealing with thickness, and thickness is considered as the variant in our analysis. So the wall slenderness, height to thickness, and the parameters that control the strain, such as axial load and wall length, as well as reinforcement ratio, which controls the crack closure during unloading and reloading, are the parameters that have been identified to be governing according to our parametric studies. In terms of experimental studies, as I said, this mode of failure has been studied using testing boundary zones that concrete columns that represent boundary zones of rectangular walls. However, there are limitations in this approach because the boundary conditions at top, bottom, and along the length of the wall are not well captured in the experiment. So in terms of wall unit testing, some experiments have been done in Switzerland and Australia. And here at Canterbury, we tested several wall specimens under lateral load as well as axial load and bending, which was applied using these actuators at top of the specimen. The parameters considered in our test matrix included thickness, length, axial load. And the wall cross sections were like this. So we decreased the length, increased the thickness, and for the specimen that had a reduced length, we increased the reinforcement ratio to compensate for the reduced lever arm and to provide the same flexural capacity as the other specimens. For the benchmark specimen, the type of behavior that we observed can be seen in this actually hysteretic curve. As you can see, we had initiation of out-of-plane deformation after 1.5% drift level, and then bar fracture and bar buckling occurred at different stages of loading, and the specimen became unstable. However, this type of instability was significantly affected by the bar fracture and bar buckling at the base, and as you can see, it was mainly localized at the base. This video here shows the development of initial out-of-plane deformation and its recovery. You can see the out-of-plane deformation starting here and then its recovery. And due to development of bar fracture and bar buckling at the base, we had a sort of, let's say, unstable base, which resulted in instability of the whole wall. So as I said, this type of instability is categorized as a local type of instability, which was actually generated by an interaction between the out-of-plane deformation and the other modes of failure, such as bar buckling, bar fracture, and concrete crushing. For our second specimen, we also observed a similar mode of failure. However, this specimen had a slightly increased thickness, and value of out-of-plane deformation that was measured for this specimen was lower. For this specimen, you can also see the development and recovery of out-of-plane deformation. You can see the large tensile strains and cracks, out-of-plane deformation and recovery, and then after development of things like bar fracture and bar buckling. This specimen, this, let's say, boundary region at the base became unstable because of progression of bar buckling followed by bar fracture, concrete crushing, all those sorts of failure modes at the base, which actually suppressed development of out-of-plane deformation and made this mode of failure rather localized at the base. So you can see the instability of the specimen, which was localized at the base. The third specimen we tested didn't have any modes of, let's say, failures at the base, and the out-of-plane deformation started in this specimen and changed to out-of-plane instability. This video shows development of out-of-plane deformation and recovery at the boundary zones of this specimen, and you can see there is no degradation observed in the load displacement plot for this specimen, and the specimen becomes unstable quite suddenly. So the out-of-plane deformation starts and recovers, and then at point D, we see an abrupt strength degradation or strength drop in this specimen, which is pretty crucial because this mode of failure can result in collapse of the whole structure since it's a brittle type of failure. The development and recovery of out-of-plane deformation for this specimen can be seen in this video. So this plot shows the history of out-of-plane deformation. The out-of-plane deformation increased and then recovered, which was successfully captured by the numerical model. So the numerical model captured the development and recovery of out-of-plane deformation for this given drift level that was applied. And then at a later stage, where larger tensile strains were generated in the boundary regions due to the increased drift level, the out-of-plane deformation started. However, since it had actually exceeded the critical strain, the out-of-plane deformation could not recover and resulted in the global, let's say, instability of the wall. So as you can see in this case, the out-of-plane deformation was not localized at the base. It happened along a specific height from the base. So the results of this specimen were used to verify the assumptions that were made in the analytical models to predict the global instability of structures, walls. We can see development of out-of-plane instability in this specimen from the east boundary. And this actually video shows development of out-of-plane deformation along the length of the wall. So you can see development of large tensile strains, out-of-plane deformation, and recovery. And this video here shows the stage where the instability happened. What I intend to show from this video is actually the extent of out-of-plane deformation along the length of the wall. So the boundary region that became unstable is the boundary region here, and you can see how the whole wall twisted and this region became unstable. So two main modes of instability were observed in our experiment. Local instability was actually observed starting from out-of-plane deformation and then formation of bar fracture and bar buckling, and the local type of instability. And then we had the global type of instability that was observed in one of the specimens. So the walls susceptible to global out-of-plane instability are the ones that are the well-confined walls that are able to develop large tensile strains along a sufficient height from the base before progression of any modes of failure, such as bar fracture and bar buckling. And the type of failure that was observed in the Christchurch earthquake is pretty much in line with these characteristics. So you can see there is no, let's say, localized bar buckling and concrete crushing, and the whole instability occurred along a specific height of the wall. The analytical model developed for prediction of this mode of failure is also dealing with this type of failure, and the numerical model successfully captured this mode of failure. And here I'm actually showing buckling of a column from an earthquake in Iran. So the type of buckling here, to me, seems to be more in line with the characteristics of this type of instability, because the buckling is rather localized at the place where large tensile strains can develop in the bars. So speaking of strain gradients, we captured the effect of strain gradients in the numerical model as well. And for this specific case, when we increased the length and shear span ratio of the wall such that large tensile strains were developed along a sufficient height, we were able to capture the out-of-plane instability. So, design provisions. So after numerical and experimental studies, in order to come up with the design provisions for prevention of this mode of failure, we did a bunch of numerical studies on walls with different characteristics and investigated the response and the failure modes and the sensitivity of the model to different parameters. So first of all, let's again see a specific cycle from loading and unloading and the out-of-plane response of walls at large in-plane curvature demands. Large tensile strains develop. So when the loading is reversed, the bars take the compression. The bars are the only elements that take the compressive forces because the cracks are wide open. And then out-of-plane deformation starts, and then cracks close on one side, and the out-of-plane deformation recovers. So there is no strength degradation observed in this whole cycle. And this yellow curve shows the history of out-of-plane deformation. And I just want to attract your attention to this change of slope here, which you know is due to pinching or the crack closure. And it is pretty much in line with the point where the out-of-plane deformation has fully recovered. However, when the out-of-plane instability starts, we observe a very abrupt strength degradation. So as I said, this strength degradation, which is pretty much abrupt and brittle, can lead to collapse of the structure because the wall, which is the main load carrying capacity of most reinforced concrete wall buildings, fail, and the structure is likely to collapse. Therefore, our limit state should not consider the critical strain corresponding to the instability mode. To come up with a new design limit state, we compared the out-of-plane response of the tested specimen with the analytical models and the stability criterion that was introduced in the analytical models. As you can see, for the out-of-plane deformations above this stability criterion, we had great, let's say, significant residual out-of-plane deformation. So we decided to consider this stability criterion as the design limit state and the, let's say, limit state corresponding to the critical tensile strain. In the analytical models, an upper bound limit was also introduced, which was the half of wall thickness, and the test observations were pretty much in line with this upper bound limit. And when the out-of-plane deformation exceeded this upper bound limit, the wall became unstable. However, the assumptions made in the analytical models about the buckling length do not match the experimental observations. As I said, in the analytical models, the buckling length was considered to be the theoretical plastic hinge length. However, the experimental observations showed that it's a parameter dependent on the strain gradient as well as the unsupported story height. And the test results show the value of 70 to 75% of the unsupported story height as the buckling length. So, for a given slenderness ratio and reinforcement ratio based on our numerical studies, the parametric studies we conducted, we came up with the critical, let's say, tensile strains. Based on these critical tensile strains, the length of the wall can be limited for a desired drift. Because as you know, for a given rotation or drift level, the longer walls will induce larger strains in the boundary regions. So with the critical strain given, then we can actually choose the length of the wall for a given drift level. So based on the results of the parametric studies we conducted, we actually came up with several curves for normalized critical strain versus slenderness ratio. So the slenderness ratio here is actually the unsupported height to thickness ratio, and the normalized critical strain is the maximum tensile strain over yield strain. And this critical strain, as I said, is associated with the stability criterion that was developed in the analytical models. So we developed these plots for different ratios of longitudinal reinforcement in the boundary regions. And then in order to consider the effect of strain gradients, we developed different charts for the stages where the plastic region is below the story level and the stages where the plastic region is above the story level. Also, we compared the results of the numerical model with the analytical models when the value of the buckling length was modified. So as I said, in the analytical models, the buckling length was assumed to be equal to the theoretical plastic hinge length. In those models, we replaced these buckling length with buckling length observed in the numerical model, which was somewhere around 70 to 75% of the unsupported height. So axial load ratio, one of the parameters that I first discussed and has been taken into account in the New Zealand code is the axial load ratio, and the minimum thickness requirement to safeguard against out-of-plane instability applies to axial load ratios greater than 5% in the New Zealand code standard, in New Zealand design standard. However, our numerical model and also the experimental results of several specimens which had different axial load ratios showed that the axial load can have a dual effect, and which is pretty much complicated. So if the axial load cannot prevent, let's say, progression of out-of-plane deformation, then it will induce an increased out-of-plane deformation due to P-delta effect and increase the probability of out-of-plane instability. So for a range of axial load ratio, the out-of-plane deformation can increase and then decrease. Therefore, so our study recommends that we actually consider the let's say, applicability of the design provisions to all ranges of axial load ratio, not only axial load ratios greater than 5%. So the main discussions, the main conclusions from this study: first of all, singular reinforced walls are more susceptible to the global instability because when the cracks are wide open and the rebars are the only elements that take the compression, when we have one leg withstanding against this compression and this actually bar yields in compression, there is no backup to restrain the, let's say, restrain against the compressive forces. So the singularly reinforced walls are more susceptible. And we did a bunch of parametric studies on the singularly reinforced wall specimen that was tested in Switzerland. The doubly reinforced walls, which are able to develop large, let's say, tensile strain along a sufficient height without progression of failure modes such as bar fracture and bar buckling, are more susceptible to the global out-of-plane instability. For design limited state, it is recommended that initiation of development of residual out-of-plane instability be taken as the design limited state and be considered for definition of the critical strain. To reduce the likelihood of out-of-plane deformation for a given slenderness ratio, so we can actually have several options when we are choosing the length. However, we need to satisfy the flexural capacities and let's say to reduce the drift level of the structure. So if we reduce the length, we have the option of increasing the reinforcement ratio in the boundary regions, or we have the option of using several walls rather than one short wall with reduced reinforcement in the boundary regions. So considering the parameters that affect this mode of failure, it's better to actually choose the option of using several short walls rather than reducing the length and increasing the reinforcement ratio in the boundary regions, because the reinforcement ratio is one of the parameters that is affecting the out-of-plane instability. So again, for the axial load ratios, it is recommended that the provisions of minimum thickness apply to the walls with all ranges of axial load ratios, not only the axial load ratio greater than 5%. And then the minimum thickness requirements would need to actually consider the buckling length of about 70 to 75% of the unsupported height instead of the theoretical plastic hinge length as the parameter. A new equation is proposed to limit the length for a given slenderness ratio and let's say a reinforcement ratio. This relationship, as you saw, was developed based on the tensile strain associated with the stability criterion, and the effect of the boundary region longitudinal reinforcement ratio is taken into account. Thank you very much. Any questions?